Hi one and all. Myself C. Pradeep Kumar Reddy and I am from Sri Venkateshwara College of Engineering, Bangalore. Today I am here to explain about Bernoullis theorem and its application. Let us look into it in detail. Introduction. The Bernoullis principle is a fundamental concept in fluid dynamics that explains the relationship between fluid speed and pressure. It is named after Swiss mathematician Daniel Bernoulli, who first described it in his book Hydrodynamica in 1738. This principle is essential for understanding the behavior of fluids in various applications from airplane wings to carburetors. What is the Bernoullis principle? The Bernoullis principle states that as the speed of a fluid increases, its pressure decreases. This principle applies to all fluids, including liquids and gases. It is based on the conservation of energy, which states that the total energy of a system remains constant. This principle has many practical applications, including in aviation, where it is used to design efficient wings for airplanes. How does the Bernoullis principle work? The Bernoullis principle works by converting the kinetic energy of a fluid into pressure energy. As the speed of a fluid increases, its kinetic energy increases, and this energy is converted into pressure energy. This causes the pressure of the fluid to decrease. This principle is used in many devices, including carburetors, where it is used to mix air and fuel for combustion. Applications of the Bernoullis principle. The Bernoullis principle has many practical applications in engineering and physics. It is used in the design of airplane wings, where it is used to create lift. It is also used in the design of carburetors, where it is used to mix air and fuel for combustion. Additionally, this principle is used in the design of wind turbines, where it is used to generate electricity from wind power. Now, we will look into the derivation of the Bernoullis principle. Consider a streamline in which flow is taking place in the direction of S as shown in figure. Consider a cylindrical element of cross-section dA and length ds. The forces acting on the cylindrical element are pressure force P into dA in the direction of flow, pressure force P plus del P by del S into dA opposite to the direction of flow. Weight of element rho g dA ds. Let theta is the angle between the direction of flow and the line of action of the weight of element. Resultant force of the fluid element is equals to mass of fluid into acceleration in the direction of S. PdA is equals to rho into g dA ds cos theta is equals to P plus del P by del S into ds into dA is equals to rho dA ds into as, where as is equals to acceleration in the direction of S, which is given by PdA minus rho g dA ds cos theta minus PdA minus del P by del S ds dA is equals to rho dA ds into V del V by del S minus rho g dA ds cos theta minus del P by del S ds dA is equals to rho dA ds into V del V by del S. Here PdA gets cancelled. Divide by rho dA ds on both sides. We will get minus g cos theta minus 1 by rho del P by del S is equals to V del V by del S. We can also write it as like g cos theta plus 1 by rho into del P by del S is equals to V into del V by del S. From figure B, cos theta is equals to dz by ds. G into dz by ds plus 1 by rho into del P by del S plus V into del V by del S is equals to 0. Here ds and del S gets cancelled because of ds is equals to also known as del S. We can write it like ds is equals to del S. So here ds and del S gets cancelled. Divide by del S on both sides. We will get g dz plus del P by rho plus V into del V is equals to 0. Above the equation is known as Euler's equation of motion. The Bernoullis equation is obtained by integrating the Euler's equation of motion as integration of g into dz plus integration of del P by rho plus integration of V dV is equals to constant. Gz plus P by rho plus V square by 2 is equals to C. Dividing G on both sides, we will get Z plus P by rho G plus V square by 2G is equals to C. V square by 2G plus P by rho G plus Z is equals to C, where V square by 2G is equals to kinetic energy per unit weight per kinetic head. P by rho G is equals to pressure energy per unit weight of fluid or pressure head. Z is equals to pressure energy per unit weight of fluid or potential head. Thank you. Now we will look into the expression for capillary rise. It is another derivation we are doing now. So introduction. Capillary action is the ability of a liquid to flow in narrow spaces without the assistance of or even in opposition to external forces like gravity. This phenomenon is due to the combination of adhesive forces between the liquid and the surface it is in contact with and cohesive forces within the liquid itself. Adhesion. Adhesion is the attraction between unlike molecules. In capillary action, the adhesive forces between the liquid and the surface It is in contact with the stronger than the cohesive forces within the liquid. This causes the liquid to climb up the surface against the force of gravity. Surface tension. Surface tension is the elastic tendency of liquids which makes them acquire the least surface area possible. In capillary action, the surface tension of the liquid helps to hold the liquid column together and prevent it from breaking apart under its own weight. Applications. Capillary action has many practical applications such as in ink pens, wicking fabrics, and paper chromatography. It is also important in plant biology, where it helps to transport water and nutrients from the roots to the leaves. Now we will look into the derivation of the expression of the capillary rise. Look into the diagram carefully. Consider a glass tube of small dimension d opened at both ends and inserted into the water, and the water will rise above the level of the liquid in general. Let h is equals to height of the water in tube. Rho is equals to surface tension of the liquid. Theta is equals to angle of contact between liquid and glass tube. The weight of liquid height h is equals to area of tube into h into rho into g is equals to pi d square by 4 into h into rho g, where rho is equals to density of liquid. Vertical component of surface tension force is equals to rho into circumference into cos theta is equals to rho into pi d into cos theta. Equating 1 and 2 equations, we get pi d square by 4 into h into rho g is equals to rho into pi d into cos theta. H is equals to 4 into rho cos theta by d rho g. The value of theta between tube and liquid is almost 0. So cos theta will become 0. So we can write it as h is equals to 4 into rho by rho into dg. Conclusion. Capillary action is a fascinating phenomenon that occurs due to the interplay of adhesive, cohesive and surface tension forces. It has many practical applications and is important in plant biology. Understanding capillary action can help us design better products and appreciate the wonders of nature.